Yeah, well, thanks for coming. Thanks for deciding to be here for this. So what I thought I'd do in this session is give you a little bit of probability theory and to emphasize some of the things that I think come up in stochastic programming. Like we use techniques from probability theories, and even though it's not sort of classically part of applied probability, I think there's a lot of things in applied probability that actually apply in stochastic programming. So what I thought I'd do is just to go through and kind of give you a collection of the results that we use in stochastic programming. So the kinds of things that come up when you're solving optimization problems under uncertainty, and you want to estimate things like how likely it is that you're optimal or how likely it is that you're far from optimal. Those are the kinds of things that are useful to use techniques from probability theory for. So what I'll do is I'll just go through some of those, and that will give you some background for some of the things I'll do later, particularly kinds of things I'll do towards the end, like the Markov Monte Carlo methods, which are popular now. And I'll also talk later about things like, there's a lot of work in machine learning now, and many people work in machine learning, and machine learning has gotten lots of publicity all over. I view machine learning as just a different branch of stochastic optimization. So some of the things that you do in machine learning, you also do in stochastic programming. We'll talk about that. And again, probability theory can contribute to that. So those are the kinds of things I want to emphasize. Okay, so what I'm going to do, I'll go through these. I sort of broke things up in different ways, but I thought I'd go through what are the basic definitions, kinds of things that concepts that we use. Like if you look at my book, my book with François Louveau, we use measure theory. I don't know, how many people have had a measure theory class? Okay, so you've had some measure theory. Okay, so we use measure theory, not that it's totally dependent on that, but it's just a lot easier to talk about things using measure theory. So I'll try to build kind of the basic definitions from that, which are things that we use in the rest of stochastic programming. And then I'll talk about common distributions and some of the properties of common distributions that we use particularly a lot. And then concepts of independence. A lot of the things, a lot of the results have to do with independent random variables. But often in reality, we don't have independent random variables. So how to deal with situations when things are not, you can't really say that things are independent. What are I'll talk a little bit about the kinds of things you can say when things are not totally independent. And then often things that we use, like when you're proving things, what are the ways in which you can prove that something converges to something else? And so in probability, there are a few of those. So I'll go through and then talk about what the differences are in those kind of definitions of convergence. Again, aim towards, what are the kinds of things that are important to be able to show in stochastic programming, and why are these, why do these relate to that? Then a little bit on stochastic processes, just where they come from in stochastic programming, what you would use them for. So this is like sequences of random variables. And then things that relate to these long-run averages. So laws of large numbers. When do laws of large numbers apply? Again, trying to emphasize what it is that what do you need to assume, and then once you relax some of the assumptions, what can you say? So what are the basic assumptions? What do you get with those? And then what kinds of things can you relax? And what results do you get from them? And then, I'll mention asymptotic results like the central limit theorem. Again, so central limit theorem, I'm going to talk about it later in the course. But central limit theorem, we often think of it like from your statistics class. You think of, oh, well, if you have 30 samples, then everything is kind of normal, right? That if you get 30 samples, then you get something that looks normal. In optimization, it's not so much the case. So in optimization, because now you're really making things correlated because you're optimizing over the collection of things. So now you're getting away from independence because you're optimizing. That's something that all of them have in common. All the samples that you have are somehow linked because of your optimizing. I'll talk about the basic results here, but kind of keep those in mind for when I talk about what happens with optimization, because different things happen. Different things can happen that give you results that differ from sort of the traditional things that, like with 30 samples, you get exactly what you want. I'll relate this to other things that you can say. So central limit theorem is asymptotic. That's something that happens in the limit. So as the limit of number of samples increases, then you get this normal distribution of the mean. In reality, again, like the 30 samples is not so bad an assumption for just independent random draws of some number. But often what happens is that, again, there's something that links them, so there's some kind of correlation. And that means that the number of samples that you need to get anything close to central limit increases, and it can increase a lot. So I'll talk about other things. So the last point about inequalities and large deviations is that there are some things that you can say even for small samples. And so I want to be able to say, even when I have a small sample, and small sample doesn't have to be like less than 30. Small sample could be anything that's small relative to dimension. So again, relating to things like we do in machine learning. So in machine learning, we can have dimension that's bigger, like dimension number of features, could be bigger than the number of samples. And none of these results, none of the like central limit theorem results are going to apply in those cases. So what kinds of things can we apply, even in a case where we have fewer samples maybe than the number of features? So that's why I want to mention those. So what are the things, other things that apply kind of independently of dimension, independently of the number of samples? So those are the last things I'll talk about, the inequalities and large deviations. Okay, so it's, yeah, so there are a lot of things here, but hopefully I'll focus on, or I'll mainly concentrate on the things that I think are most relevant for looking at stochastic optimization problems, looking at stochastic programs. Okay. All right, so just basic things. Events and probability spaces. So what we always talk about in, I'll always use this notation, like omega is the event. Omega is the thing that that triggers everything. It's not, it's just an abstract representation. It's a representation of all possible alignment of molecules in the world. So it doesn't have any dimension at all. It doesn't it's not a number. It's not. It's just a representation of everything that might be possibly revealed. And often what happens is that it represents not only now, but everything that you're going to learn in the future. So you only learn part of omega at each point in time. So it can evolve over time as well. So when I write it like this, it's like, oh, this is as if I unveiled everything kind of until the end of time. That's like wrapped up in what omega represents. But for a model, it's everything that's relevant to the model. So it's like all the things that would be relevant to the model. So it could be like whatever the demand is, whatever prices are going to be in the future, whatever customers are going to be available in the future. All those things are going to be represented in omega. So omega is not, again, it's not a number. It's just representing something. It's just representing possible outcomes. So it is, so I represent those possible outcomes as part of this space. So the big omega is the space of all the possible outcomes. Now the way to think about probability, and if you've had it in a measure theoretic kind of framework, is you take all of these possible outcomes, and then you start to split them up. And you split them up into subsets. Now the subsets are what corresponds to what information we have. So we may know that we're in a situation where, oh, it's 35 degrees out today. Okay, so we've narrowed the world of those possible future events down to, okay, now we're in this world where it's 35 degrees. And that's the subset of all these possible outcomes. So it's just one part of all the outcomes that we might be able to see. And so that's the way to think about it. We've got all of the things that might possibly occur, and then some subset of them that's like conditioning on some observation. It's like saying, oh, it's 35 degrees. Now we know this is the part of the world, part of all those possible outcomes where we are. Okay, so events are like finding out what the temperature is. And they tell us that we're in a particular part of all these possible outcomes. Now, we wouldn't have known what temperature it was going to be today necessarily. We wouldn't have known exactly yesterday. So we look at all the possible sets of events. So again, these events, these could be the set of all the possible temperatures that it could be today. And that gives us the set of these subsets. And then we represent that set of all these subsets by here I'm calling it Borel set, meaning that can take these countable unions and intersections of all the events, and I still get something that's one of the events. So we wrap all the possible subsets together and put them into this collection of the subsets. Now, what probability does is it assigns a number to those collections of the subsets. It's assigning a number to each of these subsets, saying, oh, this is how likely it is that it was 35 today. Maybe I base it on yesterday. So I've got the subsets, and then I have the collection of all the possible subsets. That's this idea of the Borel set of events. And now probability is just an assignment. So we can think of this probability as, well, how likely was it to have this event of 35 degrees again? How likely is it to have that event? And that's just some mapping of that event into this probability. So we think of probability as just taking any of the possible events, that is, any of these possible subsets, and being able to map those into something between 0 and 1, obeying a set of rules, which are down here. Okay, so probability is just an assignment between 0 and 1. That's what we think of as being how likely an event is. And so that's the way to think about probability. It's an assignment of events to a number, to a number between 0 and 1. Okay, so then formally, a probability consists of, well, what are all the possible outcomes? What are all the possible subsets of outcomes? And then an assignment of those subsets to a number between 0 and 1. So that's the probability space. So it's the set of outcomes, the collection of subsets, and then an assignment. Okay, and like I said, it has to obey certain properties. So those properties are that if the empty set has probability 0. So we have the set of no outcomes, that's probability 0. So we have to have some kind of outcome. And if I take all of the outcomes together, that has probability 1. So all the outcomes together must have probability 1. And now the only other thing I have to do is to define, well, what happens when I sort of combine these subsets together? So the other property that probability must have is if two events don't go together, in other words, if their intersection is null, then when I take the probability of their union, I just add the probability together. So as long as I get this behavior just from these kind of simple set of properties, that the empty set has probability 0, everything has probability, that is the entire set itself has probability 1, and if there's an empty intersection, then I can sum the probabilities of the union. Okay, so formally that's what probability is. Now, we think of it as like likelihood, but formally this is kind of what probability says. It's just saying, I want to see basically how much of the slice of everything is each of these subsets. And the subsets have a certain rule that when I take two of them together, if they don't overlap, then I just have the likelihood of those two things, just those two things together. Yeah. For a non-countable union, you could have, well, as long as it just adds up to the entire set. as long as you have this probability that the entire thing is 1, then yeah, you could have uncountable. But I have to have a measurable set. In other words, any set I have to be able to find the probability of it. As long as I can do that, then yeah, you could have countably infinite. Well, certainly, you can have countably infinite number of x. Yes. Okay. So these are formal definitions. I think I have probably the same sort of thing over here. Okay. So think of these outcomes, or I could think of them as samples, and that this probability is just assigning a probability to each of the possible sets. Now, if omega only has a finite number of well, you could think of all the possible subsets as being so that every element of the space, every element of the set of all possible outcomes is either in the set or not. So if you think that it could be either in the set or not, then the number of things you can get out of that is something like 2 to the number of elements in the space. So the number of these possible subsets you could think of as having a number of possibilities being like 2, that is, everyone is either in or out, power the number of possible outcomes. So that means there's a lot, and obviously if this is infinite, this is a pretty big number. But we just want that probabilities are going to be able to assign this number. So think of probability as an assignment. It's an assignment to this, each of these sets, and giving us this number that's between 0 and 1. Now, in particular, if you have a discrete, so I wrote down here like a sum, to think of like if you have a discrete set, or if you were able to make this sum from that last property down here, if this intersection is empty, that means if they're all different samples or different outcomes, then you can always just add them up. So as long as they're distinct, you can add them up, and then that gives you whatever that should be A. This is omegas are in A. Then you get the probability of that A. Yeah, so yeah, we have to assign, yeah, so if I have uncountably infinite, yeah, I won't be able to assign them. I think this may only apply actually when it's finite, right? Because even if it was countable, unless each of them had probability 0, then we wouldn't have that. But yeah, you could think of it as if these are finite, then I can sum them, and then I get this probability, as long as these are distinct. Yes, but I guess the important thing is that as long as they're distinct, you can sum them up. If it is something like a measure over the real numbers, yeah, then you wouldn't be able to make that sum. You'd have to have it's still an assignment of intervals. It would only be intervals of finite length that have probability, or have probability greater than 0. Okay. All right. So this is just the basics of the sample space. Now, this is more definitions, and I just wanted to again define things so that we kind of have things done formally. So when I use random variables, the random variable is always, you can think of, so what does a random variable do? Random variable takes any of the outcomes and then assigns them, well, it's a mapping basically of those outcomes to a number. So if I want the probability of some subset of the, let's say, the real numbers, I want that probability of that subset, what I look at is, oh, well, what's the probability, or what's the set of outcomes that map into that subset? And that's the way to think about what that probability is. So the random variable is always acting on the outcomes and then giving you something that's represented here in the real numbers. So formally what that means is that for any subset of, let's say, any subset of the real numbers, there's an event, again, a set of outcomes such that if I look at the mapping of all the things that are in that subset, I cover that subset of the real numbers. So in other words, if I'm given this B, then I can use, well, how much of C maps into B, how much of omega does C map into B? And that's the way to get what's the probability of this B. Okay, now, a lot of times like in notation, in my textbook I always use bold when I leave out the omega, so I don't say that, oh, C is actually a function of omega, a function of the set of possible outcomes. But you can think of it as that it's, well, it's always implicit when I have like a random variable. Okay, so the random variable is going to take on, let's say, real numbers. But that even while it's taking values in real numbers, what we're looking at in terms of probability is going back to the omega. So it's always back to the omega is where we find out what the probabilities are. So as I said, I keep this notation where I often use these Greek letters like C that indicates a random variable. And when you see that, and it doesn't say that there's a specific value that it's taking on, you can think of, oh, well, actually that C is shorthand for C acting on these random outcomes. So C is acting on those omegas. So then you can think of it as, okay, what is C of omega in any particular part of real numbers? Okay, so So I'll use C of omega to represent those. Now, often we'll use random vectors or even random matrices. So the random vector just means that it's a mapping from omega, but now it's in n-dimensional space. So think of this as, it's just, C is again taking some elements, taking some events in omega and mapping them in to real numbers. And we could think of that as, well, each component, each of the n different components is itself a random number. So there's a random variable that corresponds to each one of these components. Now they might all be correlated. So they could be correlated because there's a way in which, there's a common way, say, in which C takes the outcomes and maps them into real numbers. But we can think of that as each one of them is a particular random number. And if I just look at one at a time, then it's the same thing. That's just like the random variable up here. And the only reason to think about them differently as a random vector is that they may have correlation. So there may be ways in which they are linked together in terms of mapping from the set of outcomes into real numbers. Okay, now I talked here about the distribution function. So the cumulative distribution function, or distribution, most of the time I'll just say distribution function for a random variable. Just for a single random variable, I'll indicate it here usually with this capital F. So it's usually capital F, and here I'm using a subscript just to denote which is the random variable. So capital F of C is something that takes the real numbers, and again, it's a separate mapping. So it takes the real numbers, and it maps them into a number between 0 and 1. And the way to think about that is that at any point t, this f, the cumulative, or the distribution function of the random variable C at t is, again, it's a statement about subsets. So it's what is the probability assignment of the omegas in the subset where C of omega is less than or equal to t. So so this is the A up here. Like I said, it's the A that maps to B. So this is, well, what's the A that maps to everything that's less than or equal to t? The A that maps to that is the omega such that C of omega is less than or equal to t. So it's, what's the probability of this A? And that's the value that's assigned to the distribution function. So it's, again, so the distribution function is actually, it's just it's a particular assignment of the probabilities. It's the assignment that goes everywhere from -infinity up to a certain value, t. So it's that particular subset that, or what maps into that particular subset that we use for the distribution function. Okay, now if f is continuous, so if f is kind of continuously increasing in this t, then we also have a density function. So if f is kind of continuously, well, in fact, it will be continuously increasing. It's always increasing since this probability is always getting bigger. So if f is absolutely continuous, then it has this density function. So we can write f in this common way. That it's just the integral from -infinity up to t of this density. Now, if it's a discrete random variable, I could also take the sum of everything, where the sum of all of the possible values that c might take on up until it gets to t, and that would be an f. Okay, so we have the distribution function, the density function, all referring to this random variable, and then how are they related together? Well, I can always write the chance that c, so this is when this is kind of a shorthand. This is probability of a less than or equal to c less than or equal to b. You could think of this really means probability of the omegas such that 0 is less than or equal to c omega less than or equal to b. So it's that subset of the omegas. What probability assigned to that subset of the omegas gives us a c of omega that's between 0 or between a and b. And you can write that different ways. You could say a to b of df of c, or a to b of f of c when it's absolutely continuous. So yeah, any of those ways we can represent what this probability might be. Other thing about f is, again, since everything has probability 1, we know that if I take this integral of df of c everywhere from minus infinity up to infinity, then I get 1. Okay. All right. So those are those are basic things about random variables. Okay. Now I'll talk about expectation. So often we take the expectation of a random variable or expectation of functions of the random variable. Okay, so this is expectations. This is expectation of a function of the random variable c of omega. So what does that mean? Well, I'm kind of integrating. So the expectation means that I'm integrating this value over all possible values of omega. So I could write that as well. It's the integral of omega f, all possible values of omega, and then the probability that's associated with each of the omegas, which you could think of as doing this. This is kind of the basic definition of the integral. So if I use the basic definition of the integral, that it's the supremum over all the simple functions that are less than or equal to this function, and then I'll take what's the value of a simple function? A simple function just has a unit value on some interval, and then a probability that's associated with that interval. And so I'd have the supremum over everything that's a simple function below f, or the infimum over everything that's a simple function above f. All those give me whatever this integral is. So the simple functions, again, they have a fixed value, a fixed finite value on subsets that are in here I seem to use f instead of a, but subsets of all the possible subsets. So I'll have a finite value on subsets of all the possible subsets. And so that gives me something that's well-defined. It's just telling me, oh, I've got a finite value. I have some probability that's associated with that because it's a subset of the entire space of subsets. So I have a probability that's associated with that, and I have a number that's associated with that. And so this gives me a finite representation. So each of these gives me a finite representation. It's just the supremum over all those. And this is the infimum over all the other ones that are above here. So for any of these, so I have a simple way to represent each of these integrals. So each of these integrals is a sum. So we have each of these integrals being represented as a sum, and then we're taking here it's the value that's always, that is approached by everything that's below it, and this is the value that's approached by everything that's above it, above the function f. And so that gives us a formal way to describe what the integral is, or what the expectation is. Okay, so expectation is just integration, and this is the so this is the way to write the Lebesgue integral. So we're going to take expectation as the representation of the Lebesgue integral, and the only thing I'm doing is saying, okay, I'm going to apply it to these subsets. So just like you apply it to intervals on the line, apply it to subsets of all the possible sets of outcomes. And that gives you a formal way to describe expectation. And I guess the important thing from this is then this means that everything that we can say about integrals now applies to these probabilities. So it applies to expectation. So all the theory of integration now applies to expectation. So when we talk about expectation, really it's just integration. Everything that we use for integration now applies to expectation. So formally, expected value theory is just the same as integration theory. So we can use the same sort of tools, same kinds of results from integration we use for expectations. Okay, so let's talk about expectations. So, of course, the mean is the first moment. That's the expected value. Let's see. This is for a random variable, so I'll take a random variable c, and I can write its expectation. So again, this is just the function of c is just c itself. And so its expectation is what value does c have on each of the possible sets that's associated with the values that c takes on. And so I can write it this way, just the integral from minus infinity to infinity of c df. Or, again, if I have a density, then I can write it this way with c, and then the density, f of c dc. And if it's discrete random variable, I can write it that way. Again, here most of the time I use a superscript for samples and a subscript for the components, because it's mostly with vectors. Here I just used, since it was just a single random variable, here I'm just using the subscript to denote a sample, or to denote a finite set of possible values that c takes on. So if c takes on those possible values, then this is what formally what the mean is. Okay, so we get the mean. So that's kind of the most important of all the expectations. Now the higher moments, so I can take the power of c and then take expectation of each of the powers. So that gives me these different moments of different orders. And then we have central moments. So the second central moment is, so the central moments are the powers of the random variable minus its mean. So the variance is the second central moment. It's the power, the expectation of the square of the variable minus its mean. Or here, it's the second moment minus the mean squared. Standard deviation, the square root of the variance. And then another thing that we use in particular in stochastic programming is because often there are constraints that apply to quantiles. So you say distribution function at x is at least alpha. So it's the minimum x where it's at least alpha. So I drew a distribution function here. So a distribution function could have continuous parts. And then there could be a point here, like I'm drawing this eta in this case. There could be a point here where there's a discrete probability. So it might be that I have a random variable which is, let's say it's continuous up to a certain point, let's say 1. It's continuously increasing in probability up to 1. But then at 1 it takes a jump. And so it might be a discrete probability, like probability of a quarter, that it could have the value 1. So what we would see is that the distribution function then takes that jump. So the distribution function, say, comes up to a half and then takes a jump of a quarter, and then it continues to increase up until it hits 1. Okay, so the way the quantile is defined, it's the minimum x. So like this is x that I'm minimizing. So I find the minimum x where f of x is greater than or equal to alpha. So it's the minimum where when I get to f of x, it's greater than or equal to alpha. Now f of eta is up here. It's above alpha. But it's the minimum point where it is greater than or equal to alpha. So that gives me the quantile then is that point. So if this was like alpha was a half, and if there was a probability, let's say it was 0.6 up here at 1, and then 0.2 down here at 1. Well, the place where it was just above a half would still be at 1, and that would be the quantile. Now what that means is that eta is not just the alpha quantile, it's the quantile of everything from up here to down here. So it would be for every value of alpha from 0.6 down, say, to 0.1. Eta would be the quantile for that. Okay, so we can think of all these things as these are particular moments, which means that they're functions of the random variable. So the moments, the moments are anything that can be written like this. So any function of the random variable is a moment. So the mean is the first moment, and then we have these power moments, and then like this, and then central moments like the variance. But the quantile is another kind of moment. It's related to the alpha probability moment. Okay. All right. So here's just some comment. Thought I'd just do some of the things that come up in which we use in a lot of different examples. Okay, so obviously uniform 1 to n, 1 over n. Okay, so its expectation is, and this is the one you have to, so if it goes from 1 to n and inclusive, then, then the expectation is 1 plus n over 2, as opposed to n over 2. Okay, so uniform between 1 and n has the expectation of 1 plus n over 2. And then the variance is n squared plus 1 over 12. Okay, so that's the uniform distribution just from 1 to n. Now, another one which we use a lot is the binomial. So the binomial, so binomial is actually sum of Bernoulli's, which I didn't put up here. So Bernoulli is the one that's just 0 or 1 with probability p. And binomial is the sum of n independent Bernoulli's. So binomial as n, so it's like n trials, and p is the probability of each trial. And then what we say, well, what's the probability that a random variable that has this distribution takes on I? That means that there were I successes out of n trials. So it would be like n coin flips. What's the chance that I of them were heads? And then it's for each of the possible each of the comes in here, there's a probability of p to the I that they happen. That this are the ones that were successful, and then these are the ones that weren't successful. Those are the ones that had probability 1 minus p, and there are n minus I of them. And then, well, where could they occur? So there are all the possible places in which those I successes could occur. So that's the n choose I part. So we'll take the number of ways in which we can take I out of n. And then, okay, so that now, how do each of those, what is the probability of each of those? The probability of each of those is, well, it was p for all the i's that were successful and 1 minus p for the ones that weren't. And that gives us the binomial. Okay, so binomial probability is n times p, and the variance is n times p times 1 minus p. So you can do all those calculations. Now it turns out the binomial is also related to the Poisson random variable. Okay, so Poisson random variable is what you get if you have a number of trials. If the number of trials actually increases such that you're kind of continuously taking a trial, but you're dividing up the time in which you take the trial. So it'd be like I'd have a set of trials from time 0 to t, but I'm going to, let's say, change it from 0 to t to 0 to 1, and then take 1 over t time units all the way up to 1. So it'd be like if I took 1 over t, if I had t trials, and what's the probability of a success? If the probability is like lambda over t in each of those time intervals, if I do these binomial trials, keep on doing them, then I actually get the Poisson random variable. So the Poisson random variable is that at every instant, there's a chance, there's the same chance of, let's say, an event happening. And then, and each of those time intervals is independent. And then I add up all those time intervals, and I find out, well, how many events happen, let's say, in this time from 0 to 1. Okay, so if on average I'll get lambda events to happen between 0 and 1, then the probability of each of these events, probability that each number of these possible events happens, is going to be e to the minus lambda, and then this lambda to the ith power divided by the I factorial. Okay, so this is the probability of I successes, I events actually happening over an interval 0 to 1, where on average I'll get lambda events over that interval. So again, it'd be like if I took lambda is going to happen between 0 and 1, and I take lambda over t as the probability in every interval, and I take that lambda over t and put it in here, and I take t to infinity, then I'll get this expression down here. Okay, so So Poisson is another sort of common thing. What's interesting about Poisson is, so if you kind of put that in here, this was lambda over t, and then that was t, then I'd get lambda, and this is 1 minus lambda over t, but t goes away, so I just have lambda. The variance is just lambda. So we have its expectation is lambda, and the variance is lambda. Okay, those are the most common discrete ones. For continuous random variables, uniform is just the extension of the discrete uniform. But here, actually, the expression is a over 2. So it goes between 0 and a. Then it's a over 2. And the difference from what I had before is it was 1 to n. So this one's 0 to a. OK, so 0 to a goes a over 2. And then variance is a squared over 12. And now exponential. So the exponential with rate lambda. Now this is, we could think of this as the time between events for the Poisson. So how long does it take between an event of the Poisson random variable? Well, on average, it's 1 over lambda. So the exponential with parameter lambda, which has this density, and its values are just greater than or equal to 0. It has a mean, so this would be like the time between the events of the Poisson is 1 over lambda. And now, of course, the exponential also has the property that it's memory-less, meaning if you condition, if you say, C is greater than or equal to some value a, so if I condition on it being greater than a, and a is anything greater than 0, the expectation conditional on C being greater than a is still 1 over lambda. So that the expectation never, the conditional expectation of being greater than whatever point you condition on is always 1 over lambda. So it doesn't, in other words, the time that it's taken never makes any difference. Okay, and here's the Gaussian or the normal distribution with mean mu and variance sigma squared. What did I put on gamma? I use gamma a couple times in the book, mainly because gamma, it gives you a range of values, so it gives you kind of a different range of values. And it has 2 parameters. So exponential has 1 parameter. The uniformly 0a has just 1 parameter. Normal has 2 parameters, and gamma also has 2 parameters. The gamma parameters determine both the mean and the variance. So the mean is alpha times the beta, and the variance is alpha times beta squared. But for estimation, we only have to get 2 things. So for normal and for gamma, we're just fitting 2 things. So essentially, you're fitting scale, and you're fitting shape in some way. So scale is like mean, and shape is like the variance. But the same thing with the gamma distribution. Okay. Okay, I mentioned conditional expectation. So, formally, what does conditional expectation say? It says if I am restricted to a set, so if I'm going to restrict things to A, then I'll take expectation just over that, in other words, I'll just integrate over that particular set, but then I'll divide by the probability. Okay, so, so this would be formally in terms of omega, where I'm conditioning on particular sets of omega. If it's, if I'm conditioning on values that the random variable takes on, then my A is actually whatever the set of outcomes is that gives me values in this subset B. So conditional expectation is also related to independence, to say that two random variables are independent if, when I condition on, let's say, particular events of one random variable, it doesn't affect the expectation of the other one. So if I condition on one random variable having a particular set of possible outcomes or possible values, that doesn't affect whatever the expectation is of the other one. And uncorrelated, so independent random variables are uncorrelated, but there may be variables that are uncorrelated that are not independent. So two random variables are uncorrelated means that if I take the expectation of their product, I just get the product of the expectations. So taking the expectation of the product is just the product of the expectations, or the covariance of the two is equal to 0. Okay. So as I said, if two random variables are independent, then they're uncorrelated. But the opposite isn't true. So in other words, you could have two random variables that have covariance of 0. In other words, if I take the expectation of x times y and I subtract off ex, ey, I get 0. But they're actually not independent. That is, there are particular values of one of them that will change the expectation of the other. And you can think about examples like that. So I think if I had a variable that's between -1 and 1, and then I square that variable, which gives me something that's only positive. So if y is like the square of the other one, they're uncorrelated, but they're not independent because one's just a function of the other one. So when we say uncorrelated, that actually means something different from independent. That's the main point of this. And just a couple of things about taking expectations. So often it's useful to sort of do conditioning when you take expectations. So in other words, if you wanted to take the expectation of these two random variables, it may be difficult to do that directly. So it may be hard just to say, figure out what's the expectation of these two things. However, you may be able to do it conditionally. And that is, often what you can do is you can condition on one of the random variables and say, okay, if I know that this one takes on certain values, then I can take the expectation of x. So we'll find, going the wrong way. So we'll find this, and then now I can take the expectation of the other part. And a particular place where that's important is, this is often called Valt's theorem. If I have a random sum of random variables, I can take the expectation of those random variables for a given value, in other words, for a given n, and then I can take the expectation of that n. So if each of these is independent, that'll be just like mu, and then, okay, now I can just take mu times what's the, whatever n is, whatever the expectation of n is. So you can do those two things separately. So you can take the expectation conditional on the value that n might take on, and then take the expectation over what the possible n's are. So in other words, I have mu times n, and now, okay, now I can take the expectation of n. Now mu times the expectation of n. Okay, so those are useful things just to often, because we don't know exactly how to do this directly, but we can do it through conditioning. Okay, I said I was going to mention different things of convergence. Okay, so often what we have is, we'll have a sequence of random variables, and those sequences are probably related, and they might just be a set of observations. So I might have a set of observations of some random variable that I don't really know very much about, and I'm trying to use that sequence to come up with what I think that true random variable might be, or what its mean might be. So we take a sequence of these random variables, and we want to see, well, when does that sequence actually converge to the random variable that we're interested in? Or often we're asking questions like, well, how far is it? How far is it from what we're really interested in? So if I'm interested in what this random variable is, and I want to find out, well, how far is this from that random variable? So when is it that this random variable is going to converge to this other one? Okay. Okay, so there are basically three ways in which they can converge. And I have them here. Well, I have the sort of the tightest one at the top. So we say almost sure. Almost sure means that convergence occurs with probability 1. Or, in other words, the only place where it can't occur is a set that has absolutely 0 probability. So almost sure convergence is the strongest form of this. It's saying that the only time that it doesn't happen, that if I look at how does X map omega to how Y maps omega, all of them are going to be mapped exactly the same way by whatever the limit of these xi's is. All are going to be mapped exactly the same way, except for whatever happens on this set of probability 0. Okay, so almost sure convergence, that's the strongest one. So like I'll mention law of large numbers in a minute. So when we say strong law, strong means almost sure. So strong is, this is like almost sure. That's what that strong part means. Now, in between, there's one that says with probability 1. Okay, so this one's saying that there's like there's like no possibility that I take the limit and I'll not end up being exactly where y is. So with probability 1, it says, well, the probability that you're not getting the same thing, in other words, the probability that these two things are going to be different by more than some epsilon, that probability is going to go to 0. That's essentially what probability 1 says. So the probability that these two are going to be different is going to go to 0. Now it doesn't exactly say that this is only a probability 0 event where they don't match each other. It's saying that that probability that they don't match is going to 0, but it's not saying that it's always going to be 0 at the very end. So this is not quite as strong. So you can show almost sure convergence is going to imply this convergence with probability 1, but it's not necessarily true that this implies the other one. So so you don't always have this part, even if you have this part. And now the last one is probability or convergence in distribution, or often it's called convergence in law. So convergence in distribution or convergence in law says, at least this is just for random variables, if I just take points where the function, the distribution function is continuous, then there's convergence at those points. So at the points where it's continuous, I get convergence. Now this is a little bit, you can show that, well, this obviously is going to be implied, it's going to be implied by this. It's going to be implied by this as well. So convergence in distribution is actually the weakest of these. So this gives a hierarchy. It says the strongest kinds of convergence is this one up here, where the only way that it doesn't converge is when it's a set of measures 0. In between, there's this convergence that occurs, well, where the chance that that they're not the same is getting smaller and smaller. So the chance that they're not the same is converging to 0. And that's the one that happens with probability 1. And then this one down here is saying, well, if I just look at points where it's continuous, I have convergence of the function values at those points. Okay. All right. So that gives us ways in which we can talk about convergence. And those are also related to these stochastic processes. So stochastic processes are representations of sequences. Now usually, well, to be a stochastic process, all it has to be is a sequence of random variables. It's a sequence that's indexed by something. Usually it's time. We often think of them as being indexed by time. But it could be any kind of index set. So we have a sequence of these random variables. The only thing that binds them is that they're all acting on the same omega. So they're acting on the same set of possible outcomes. And usually it's all outcomes. Often what we think of is that they're sort of getting more and more information over time. So if it's a sequence that's increasing, that the information is increasing over time, is they're actually getting refined on the set of possible omegas that they apply to. Okay, so formally then a sequence, a stochastic process is a sequence of these random variables that define a probability set. And often it will be such that as I get more, so if I is indicating time here, as I get more information, so as time goes on, I just get richer and richer information, which means more and more subsets. So the set, these are the number of subsets that I can get information about, which would be like the temperatures of multiple days. So I know the temperature of a day, I know the temperature of tomorrow, I know the temperature of the third day. all of those are giving me more finer and finer information about the set of possible futures. So I get more and more information. This is called the filtration of the events. So as I get more and more information, that means I have more and more of these subsets. Okay, so particular stochastic processes that are of note, things that are Markov that only depend, so that the probability that any of these random variables would be within a given set, that probability can only, or would only vary with the previous observation. So if I condition on all the observations that happened up until time I, it would only depend on observations up until time I minus 1. So everything is contained in whatever the value of the process was in that previous time step. So Markov process, these are related to stationary processes. Stationary processes are just ones where the index of time sort of doesn't matter. So the probability that if I take a given sequence from the time, or from the stochastic process, so a given sequence of observations of the stochastic process, that given sequence doesn't change if I shift the time of when it started. So if I take it from here I to I plus k, if I shift it by a given number j and go j to k plus j, k plus I plus j, that's not going to change things. So then that makes the process stationary. Okay. Yeah, and as I said, so we could think of the sequence of random variables that's associated with the Poisson process like the times of the inter-arrival times. So the inter-arrival times, they're drawn from an exponential distribution that has a given mean. All of those are actually independents. Those would be both stationary. They're kind of trivially Markov because they just depend on, they're independent, so they don't depend on any of the previous observations. Okay, so those are sort of common stochastic processes. So I said laws of large numbers are important. So I stated the two laws, but they're essentially the same thing. Okay, so if I take independent observations, so x1 through xn, so this is a sequence. They're independent, identically distributed, and they have a common mean, right? They're identically distributed. Okay, so all I need is that they have a mean, a finite, well, in this case, a finite mean. Okay, so there's no, at least for the first, there's no assumption about how widely distributed they are. So they don't have to have a variance. They don't have to have a finite variance. The variance could be infinite. So yeah, it could be something like 1 over x squared. Doesn't have a variance. Okay, so but all they have to have is a mean. So as long as they have a mean, and I take independently and identically distributed random variables, if I take their average, then the weak law of large numbers, this is like the with probability 1 statement. the weak law of large numbers says that this average, the chance of the average being different from the mean of every, if I took all of the possible values, the chance of that sample average being different by more than epsilon is going to 0. So in other words, for any epsilon, any delta, once I go beyond some point, there's always a point beyond which the probability that that sample mean is different from the true mean by more than epsilon is going to be smaller than that delta. Okay, so this is convergence in probability. Okay, so the weak law of large numbers is this convergence in probability. It just says that this sample mean is getting closer and closer to the true mean. Okay. Now it turns out that with these conditions, and in fact I don't really have to, if I maintain independent identically distributed and have a finite mean, I can also show that there's a strong law that applies. That is, in other words, that this convergence is not just with probability or in probability or with probability 1, but that it is almost sure. So I have almost sure convergence as well. That is that the only time that if I take the limit of the difference between the sample mean and the mean, the only possible sets of omegas for this determining what this value is are a set of or probability 0. So everywhere except for a probability 0 set, this has to happen. Okay, so that gives us the strong law. Now, as I said, these can be generalized. There are a lot of situations where things are not IID. And in fact, we need something like that if I take the sum of covariance across time, I get something finite, something like that. So I don't have a lot of really strong dependence between events. Then we'll end up with kind of similar results. So these are, and sometimes you can only show the weak, but most of the time you get both weak and strong versions of these results. So I guess the point is that there are many non-IID situations where these things apply as well. Oh, went the wrong way. Okay. Okay. So strong law. Now, strong law is again an asymptotic result, but it's saying in the limit as the number of these samples becomes larger, we're going to get convergence of the sample mean to the mean. So the central limit theorem is stating something stronger. It's saying I've got independent set of these observations. They all have a finite mean, plus they have a finite variance. So we need finite mean plus finite variance. Now this can be relaxed as well. You can relax it, again, it's something like that the covariance between xi and xi plus t goes to 0 quickly. So in other words, like if I summed up those covariances over t going from 1 to infinity, I get something finite. So if it is finite in that way, then we also get this kind of result that says if I take the sample mean relative to the true mean and I multiply it by the square root of n, I get a standard normal. with variance of sigma squared, whatever that sigma squared was. I get a normal distribution with that variance. Or in other words, that the standard deviation of the sample mean minus the true mean, or the sample mean minus the true mean, is a normal with a standard deviation of sigma divided by the square root of n, and mean of 0. Okay, so as I said, this result is asymptotic. So I mean, the strong law results are also asymptotic. Most of the time, this, so most of the time, this result's going to hold, that's kind of very generally. But in optimization, it often happens that it takes a really long time for this kind of result to actually occur. So most of the time, if I just take independent samples of anything with a given mean, as long as n is greater than like 30 or so, this result is pretty good. It will give you something very close to what you see. But in optimization, it may generally happen. And the problem is that optimization creates dependency. It creates dependency such that this idea of having correlation that actually is going away, the correlation that's induced by optimizing is not going to go away. And that's always going to be in the optimization. So that's kind of the, let's say, that's the key thing to remember about central limit theorem here, that when we do optimization, it has different implications. It will have different implications. Okay. Now, what I wanted to mention are some results that don't require asymptotics. So these are mostly like large deviation kinds of results. These are results that apply very, very generally. So like the Markov inequality. For a non-negative random variable, the probability that it's bigger than a positive number is less than or equal to its mean divided by that number. Okay, so this is a result that doesn't depend on any asymptotic results. We can estimate certain probabilities using something like the Markov inequality. Or the Chernoff bound. So the Chernoff bound, you can think of it, it's the Markov inequality, but applied. I take any random variable and I take I put it in the exponent. In other words, I just take e to the x. E to the x is always non-negative. So e to the x is a random variable that satisfies the Markov inequality. So now I can use the Markov inequality for e to the x. In fact, I can take e to the anything times x, anything positive times x. So e to the tx is another random variable that I can apply the Markov inequality to. And therefore, the probability that x is greater than or equal to a is less than or equal to the expectation of any, the expectation of e to any power of that random variable divided by e times t to the e times t, or power e, power t a of e. Okay. Now these things also lead to these large deviation type bounds that if I have a sequence of random variables, has a given mean, has finite variance, then the probability, now this is something that applies generally, the probability that the sample mean is bigger than the true mean by a certain amount is going to decrease exponentially in the number of samples. So there's always some values that are going to give this result. And again, this is independent of, this is non-asymptotic. This is for any n. But the only condition is that, I mean, alpha and beta. Knowing what alpha and beta are is often quite difficult. So it's often quite hard to actually get what those values are. But actually, in some cases, we can do it explicitly. I'll mention there's I have one result of this kind for stochastic programs where I know I can exactly say what alpha and beta are. But those kinds of cases are relatively rare. Okay. Okay. So this is just to wrap up. What all these probability results are about is finding what's the distribution of optimal solutions, what's the probability that a given result is optimal, or if it's close to optimal, and then what's, for a given solution, what's the distribution of potential objective values. So this is like if I have an optimization problem where some of the parameters are random, what's the distribution that induces over optimal values? How likely is a solution to satisfy a set of constraints? How can you construct solutions? And in particular, this would be like taking samples. How can I take samples to construct a solution that matches the distribution that I'm actually trying to achieve? And what happens as you add in more samples? So those are all the kinds of things that we talk about in stochastic programming. And so with that, I'll wrap up unless you have some other questions. Okay. Well, thanks. So I think what will happen is, we're going to I have some problems that you can work on. And I think Joydeep tomorrow is going to go over more convex functions and properties. And then I'll do like introduction to stochastic programming, and then we'll talk about models. And then later I'll get into how we use these probability results in trying to just say, these kinds of questions. What's the likelihood of an optimal solution? How can I say how close I am? What's the probability that I can assign to optimality or to feasibility at these given points? Okay, all right, thanks. No, I guess I won't be here, or I won't be teaching tomorrow, but Joydeep will be teaching tomorrow. Okay.